Hey guys, welcome back to our next lesson. Today we're going to look at another form for complex numbers, and it turns out to be super useful, and we call it polar form. Our mindset message for today is that math makes sense, and I choose this for this one because this lesson really ties a lot of what we've been learning together in really important ways, and these different things like trigonometry and complex numbers and radian degree measure and all these things, the way they tie in with each other ends up helping us understand each of those pieces more deeply, I would say. So today we're learning to plot and convert between rectangular and polar coordinates. Remember, rectangular coordinates are our regular like x, y coordinates where you move over and up or down or whatever. And then we're going to learn to write complex numbers in rectangular form or polar form. We've already studied regular form, the rectangular form. That's like x plus y I. Prior knowledge, remembering radian and degree measure, specifically sine and cosine, and thinking of them as coordinates on the unit circle, but just working with them in general, as well as the stuff we've been doing with complex numbers. Let's dive into our very first question, I guess I would say. And no, this is not a trick question. It is a very basic, simple question, but we're building a foundation here. So suppose you, Patrice, are standing at point P in a field, and you want to get to your long-lost love, Quentin, who is over here. How would Patrice move to get to Quentin, most logically? And again, no, this is not a trick question. You're likely to say, well, what do you mean? Patrice would face in Quentin's direction, right? She'd turn to face him, and then she would walk directly towards him. That's the most efficient way, right? The interesting thing about this, though, is so far in your experience in math with coordinates and locations, we've used coordinates to help specify a location, and especially to help us understand the relevant distance and position of two things. So oftentimes if I'm starting somewhere, I consider that the origin. If I had started this question that I asked you and I had placed an x-y axis here, I'll bet you might have answered it differently, possibly. You may have said, well, to get from P to Q, I noticed that Mr. Engel put an axis here, so I'm supposed to move over this far and up this far. And this we'd call x, and this we'd call y. So this point where Quentin is at, and actually let me just erase this for now, we would call the coordinates of Q x comma y, okay, because of this movement, right? But this question we asked is a very interesting one because it lends an idea to us for a different way to get to the same exact point here. And that ties in with circles and trigonometry like we've been studying. Another way you could think about getting to point Q instead of going over and up, even in this coordinate system, would be to rotate a radius, I say. You rotate however far of an angle you need, we'll call it theta again, and then you go a specific distance. Now this isn't the unit circle anymore, right? If you think of this as a circle here, we'll just label this R for radius because that specific distance is the distance that Patrice will need to walk to get to Quentin. What is better about this? It's actually more efficient in many ways because, first of all, R is a smaller distance than the total of x and y together. That's just a true thing about right triangles, right? The hypotenuse always has to be, well, actually any triangle, one side always has to be longer than the combination of the other two sides, right? So this idea forms a very core important foundation to what we're going to be studying through this lesson. Let's go ahead and dive into some very specific ways that we need to be able to work with these two types of coordinates. Okay, so our main vocab for today, any point in the plane can be represented by either rectangular or polar coordinates. The new one for us is polar coordinates. I've made kind of a little table here because we need to learn what it means to plot a point in each format. We're already familiar with how to plot a rectangular point, right? x comma y means to move horizontally by x and vertically by y, and then we'll land at the point we want. However, a point in polar coordinates looks like this, r comma theta. So they represent something different. R represents the distance away from the origin, and theta represents the angle of rotation. So in general, to plot a point, and we'll do an example, you move out however much the radius is, and then you just rotate by however much the angle says to rotate, and then you land there. So I like to think of this simply as rotate a radius. That's a nice little phrase you can remember. But we need to talk about one thing that's helpful is to be able to convert between the two. Now, the cool thing is we're going to connect this with complex numbers soon, which makes this conversion even easier, but it's still a standard thing people talk about to look at it this way. Now, luckily, we've already done this before. It actually isn't new at all. If I know a point in a rectangular and I want to figure out what the polar coordinate is, I need an r and I need a theta, right? Well, let's look back to our diagram before. How does this r relate to x and y if I know the x and y? Oh, Pythagorean theorem, right? So r squared is x squared plus y squared, which means r is equal to the square root of x squared plus y squared. So there's a conversion. You can use x and y in order to figure out what r is. And same deal as we've done before. If we know x and y, that relates to the tangent ratio, right? And so theta is going to be the inverse tangent of y over x. But remember, that's only for quadrant 1. You have to be thoughtful, like we learned in our last lesson. If it's in another quadrant, you have to adjust after you've used the tangent inverse, right? Depending on what quadrant you're in. And if we want to convert from polar coordinates to rectangular, I want to remind you that x is always equal to cosine theta, and y is always equal to sine theta. In fact, we can always write the coordinates as cosine theta, sine theta. The only problem here is that's in the unit circle directly, which has a radius of 1. But if we've got now a radius of r, not 1, essentially we've scaled that triangle by r. We've multiplied everything. So it's simply, since that multiplied by r, this and that also must. So we're just going to say the new coordinates are r cosine theta and r sine theta. So there's a direct conversion we can use if we want to go from polar to rectangular. Now let's actually get a little bit of practice graphing and thinking about these coordinates, and then we'll look at how they relate to complex numbers. All right, let's just get some straight up practice converting first, and in this one you'll also be asked to plot. Just remember, rotate a radius, right? Go ahead and pause right now, and then we will look at this solution together. All right, let's see what you got. So again, we're just using the formulas. Since this is rectangular, we need to figure out what is r and what is theta. So we just use our conversions. So you should get root 73 for r, about 8.54. And then this one, remember, is a little tricky, so we'll talk through it again a little bit. You'll notice your calculator, if you do the tangent inverse, spits out negative 69.44. That's talking about this angle, but again, we typically are measuring angles from the positive x-axis and rotating around, right? So if you think about how that relates, the orange angle can be gotten by taking 360 degrees and subtracting 69.44, right? So if you do that, we get about 429.44 degrees. So our actual coordinate pair in polar coordinates is root 73 or 8.54 comma negative 69.44. If you want to be perfectly accurate for the angle, you would have to write 360 minus tangent inverse blah blah blah, but it looks a little nicer like this. Okay? So the other one here, probably a little more straightforward. You can simply just put right in there. So r cosine theta and r sine theta, and so you should get 2 root 3 and 2, and that should be your coordinates for that one. Whoops, we forgot to actually plot this. So remember, rotate a radius. So we need the radius. Usually I find it's easier to do the radius first and then rotate. So if we just mark this out at 4, and then we rotate by pi over 6, then we will reach the point 4 comma pi over 6. Now this is actually super important and it'll lead into our next example. So let's go ahead and actually just look at our last example for part 1 here. So a big important idea here, it turns out that polar coordinates aren't unique. Remember, unique means it's one of a kind. So in a rectangular coordinates, if I tell you the coordinate pair, let's say 3 comma 8, you know it's over 3 and up 8. And there is no other coordinate pair that is at that same location. Polar coordinates are actually different because if we consider this as a circle here, so let me just draw the full circle with radius 4. There we go. You know that we went out 4 and then we rotated by an angle of pi over 6, right? But isn't there other radii or maybe another angle that would get us back to that same point again? So let's look at a few of them. You agree that if I go 4 pi over 6 we're good, but what if I went from there and I just did another full rotation? Technically that's actually a different angle, isn't it? So we could rotate 2 pi as far as we want from there, couldn't we? So technically 4 comma pi over 6 plus 2 pi n. And this n stands for an integer because if we're at pi over 6, I can go this way 2 pi or I can go that way 2 pi. So n allows this to be positive or negative, and remember we always mean for n to be an integer. So this actually represents all the possibilities of equivalent points. One side note, you might be thinking, well, what if the radius was negative? It has become convention to make the radius always positive because the way that this connects with complex numbers that we're going to talk about next makes everything work much nicer, and you can still achieve any point you want by always forcing the radius to be positive. Plus it makes sense, and we're talking about a circle, thinking of it as positive is important. If we did allow for negatives, you could technically go back 4 and then rotate like this much, or you could go back 4 and then rotate around by that much. But for now, I'll just let you know that it's convention to just leave r positive. So that's the end of part 1. Now we're going to build some important connections, the most important thing I think for this lesson, to complex numbers, as I've mentioned.